We're going to redo this question. So this was a question where there's a laminated steel section in this magnetic circuit, and then there is also a cast steel section. So we're going to call this sort of laminate for L for laminate and C for cast section. And that is a series magnetic circuit. And we did a big long solution that actually took a whole hour. And we approached this problem. It says find the magnetomotive force that produces a total flux of this given amount of flux. So what we did before, and you can look at the video of us doing this before, we said, what was the magnetomotive force? We use this equation. Flux is given, and we had to calculate the total reluctance to use this equation. And then in order to do the total reluctance, it was our total equals R of the cast section plus reluctance of the laminated section. So instead of that, we are going to do something different. And that was actually an hour-long solution, but normally our brains first go to that equation. Now we are going to solve it this way. So this is like solution 2, which is quicker. So instead of doing reluctance, we're not going to do reluctance at all. We're going to use this, that the magnetomotive force total is, we're going to exploit the fact that this is a series magnetic circuit. It's going to be the magnetic motive force of the cast section plus the magnetic motive force of the laminated section. So we're going to use this. And we know that magnetic motive force is a little used equation is the mean path length times magnetic field strength. So we're going to exploit that relationship that is actually very rarely used. Okay, so the total magnetic motive force then is LH plus LH to add the two sections of the cast and the laminated sheet steel. And that's going to be our total. So what we have to do is, of course, we have to find the mean path length and the we're going to have to find the mean path length and the magnetic field strength of both of these sections. Okay, so let's go and divide this up then. This is the cast section. And then we have the laminated section. First of all, to find mean path length. Well, mean path length is the length of the cast section will be the middle of where it's traveling here. So here's sort of the outline of this this cast section, and it's sort of the middle here. If I were to draw it straight on, then the mean path length is the middle here, the middle here, the middle here. And so that length is, there's quite a few ways of doing it. I could just take the exterior dimensions, all of the exterior dimensions of it, which is, if I were to add them all up, they would be the 2.5 plus 15 plus another 2.5, which is 40. And then I could do the interior as well. I could add the interior dimensions, these interior dimensions, which is 10, 20, 30, to the exterior dimensions and divide by 2. So let's do it that way because that's different than my other video. So I could say the average of exterior perimeter plus interior perimeter. And then that would give me this middle, right? If I do the 12.5 and 15 and 12.5 is the exterior, 10, 10, 10 is the interior, and I divide those by 2, that would give me the average. So 1/2 of exterior is 12.5 plus 15 plus 12.5. What are we working in? Centimeters. Plus, let's see, 10 plus 10 plus 10 centimeters. And I'm going to add those two and take the middle path of them. So divide by 2, which would be, if I were to add all of that up, well, I'll put another step, 1/2 of 40 centimeters plus 30 centimeters. So 1/2 of 40 plus 30 is 35 centimeters, which is kind of useless to me. I like things to be in meters for all of our magnetic circuit calculations to work out. All right, now let's do the laminated section. Why do I need LC? It's to just go into this formula. So L of the laminated section, well, the laminated section is just a rectangle. So it's really, oh, it's not like that at all. It's not just like that. It's this middle section, plus it goes up a little bit, plus it goes up a little bit. So the laminated section really, let's see, what is my dimension here? In here, it's 10 centimeters where it's open. And this is 15 centimeters. So this must be like 2.5, 2.5, and we have 2.5. So that's what my mean path length is looking like. So if I were to calculate that, again, I can go sort of like the exterior plus the interior and divide it in half if I want to, but it really is pretty straightforward. I can see here that it's going to be, it's just going to be 15 centimeters because this size is the same as this size, right? And so instead of it being here, I'm moving it to here. It's like moving it to here. So it's really just the 15 centimeters. So it's hard for me to even explain it. But if you want me to do it in the way that I did before, I could say average of exterior plus interior. And I could say that's 1/2 of 20 centimeters plus 10 centimeters. And 1/2 of 10, and so that would be my 15 centimeters, which I can just kind of see, or 0.15 meters is better for us. And now we have to find H. So how do we find H? H is a little bit harder to find than our geometry. And H only really exists for us sort of, in one way. And that's if we know the permeability. So find H of the cast section, find H of the laminated section. Well, we know that the permeability of the cast section is going to be the density, the flux density of the cast section over H of the cast. If we can find this permeability, then we can find H because we have BH curves. And BH curves, if we need to re-explore that, we have lots of resources and videos for that. BH curves is the slope of the BH curve is where you get permeability. So this is known for cast material, and then it's known for laminated steel as well. All right, so what do we do here? So do we know B? Well, we know that flux density is equal to the flux over the cross-sectional area. We know flux, we kind of know the cross-sectional area as well. So if I were to take the cross-sectional area of this up here, and I were to pull a plane of that cross-sectional area, then I know what the area is, where area is equal to, I see up here, it's 4 by, it's 4 deep, and then it is 2.5 this direction, 2.5 centimeters in this direction. So it looks like this. It is 4 centimeters by 2.5 centimeters. So cross-sectional area, 2.5 times 4.0, if we're keeping our significant digits, equals 10 centimeters squared. If I had room, I would have put centimeters in there and centimeters again to remind myself that it is centimeters squared. And 10 centimeters squared, make sure we do this conversion properly, because if we don't want centimeters squared, what do we have to multiply by to get meters squared? Well, there's 100 centimeters in a meter, but there's 100 squared in 1 meter squared. So we have to make sure that we do that conversion properly. So what this ends up to be is 1.0 times 10 to the negative 3 meters squared. Okay, and same with over here. I want the permeability of the laminated steel, which would be the flux density of the laminated steel over H in order to find H of laminated steel. I know that the flux density is the flux, which is given divided by cross-sectional area. Therefore, I have to find the cross-sectional area over here. Well, this one's a little bit harder because the cross-sectional area, if I were to cut the laminated steel up here, then I would see that it's actually like this with laminations when I cut it. And the laminated steel is the 4 centimeter dimension is actually times 90% because 10% of it is laminated. Only 90% of it is actually steel that does a, work in this magnetic circuit. So I actually only take 90% of the 4 centimeters in that direction. Laminated, 10% laminations. So you don't take that 10%, you only take 90% that's actually sheet steel. And in the other direction, I can take the 2.5 centimeters. So area cast then, in this case, is area cast in this case is 2.5 centimeters times 90% of 4.0 centimeters, which, and I'm squeezing it in there, which is 9.0 centimeters squared. And if I were to convert that to meters, just like I did over here, and remembering that that centimeter has to be squared as it's converting to meters squared, then that gives me 9.0 times 10 to the negative 4 meters squared. So at this point, it's nice. I have AC. So I have A, I have flux in the question. So I have flux, I have A. So I can now find beta. So the flux density then, therefore, beta is equal to the flux over the cross-sectional area. Oops, this is L. And over here as well, beta equals, the flux density is the flux over the cross-sectional area. Flux is given in the question. It's 1.2 times 10 to the negative 3 Webers. And over here, it's 1.2 times 10 to the negative 3 Webers. This area is 1.0 times 10 to the negative 3 meters squared. This area is 9.0 times 10 to the negative 4 meters squared. And I'm doing this side by side so that you realize that in a series magnetic circuit question, you're just doing the same thing over and over and over again. So we might as well do it at the same time. Then we're going to add up later. Okay, so the laminated section ends up being 1.33 Tesla. And the other ends up being 1.2 Tesla. So at this point, we need to look at the BH curve for cast steel. Look to the BH curve cast. And here we look to the BH curve sheet steel. So let us do that. And when we do that, which you can look up on the internet, you can find in textbooks, etc., will see that there is a relationship between flux density and magnetic field strength. Flux density and magnetic field strength. That goes something like this. And now you're going to find that beta of 1.2, and you're going to go over and down. You're going to find the 1.33, you're going to go over and down. And what you'll find that you hit is, in this case, if you have a flux density of 1.2 Teslas, it means that the magnetic field strength of that cast section must have been 1,220 amp turns per meter. I'm going to say from curve. And I'll leave that as an exercise for you to find a curve that is going to be your reference and find that. And if there was a flux density of 1.33 Tesla over here, it would correspond to a magnetic field strength of 900 amp turns per meter. So now we know H. H is up here. H is up here. We know beta. And what was I saying in the first place? I was saying this is a shortcut to the problem that took us an hour last time, because we are going to use this equation. So let's use that equation. Let's go back to our dark blue and use that equation. Well, that equation is simply, oops, running out of room. We better be done pretty fast here. That equation is simply Fm equals, so Fm of the cast equals H cast times L cast. Fm of the laminate equals H laminate, L laminate. And we just got H is 1220 amp turns per meter times L was 35. It was 35 centimeters. It was 0.35 meters. And over here we had 900 amp turns per meter. And I hope this took less than an hour. And what did I have for mean path length over here? I had 0.15 of a meter. So that left me with 427 amp turns. And over here, the magnetic field strength, or sorry, the ferromagnetic force is 135 amp turns. Now, therefore, the force of the entire circuit is, having trouble writing down there. Therefore, force total. Oh, we have run out of time and space. Total is equal to, and I'll just shortcut it here, 427 amp turns plus 135. Hopefully you're following me. It's just the sum of these two that we just wrote. And the F total is 5.6 times 10 squared amp turns. And so I just want to remind you again that the way I approached this problem is I did not calculate the reluctance like we usually do. I just went straight to the force calculation, and I realized that this is a series magnetic circuit, so I can add the forces from each of the sections, and I can always get this force from this obscure and rarely used equation where the magnetic field strength times the mean path length is equal to the force. So I just added them up, and I got what I hope is the same answer that I got in the big, long 1-hour video. I also hope this took less than an hour. So that's a really handy way to do a shortcut if you are on an exam for magnetic circuits.